Let me just check if you're live. Yeah, okay, you're live. Fine. So I'll come to the week 12 live session for your course Intro to Machine Learning. And as requested, we'll do the this question first. We have a question on LDA. So people who were there in this session when we solved this, do you guys want to take a crack at this? How is which like when we solve this, so what do you think is the answer and what's the reasoning behind it and so on? You guys can see the question though, right? So we have two conditions. One is we have two classes in the data set, one with mean 0 and 5, variance 1 and 2. And here it is mean 0 and 1, but variance is 2 and 3, right? So, so any ideas how you would go about solving this question? No ideas? Have you forgotten LDA or what has happened?
Hello.
Yeah, go ahead.
Yeah, so probably if I recall the reasonings from there, I think we have to check how the distributions, how means these first are the distributions. If there is sufficient overlap, then we can probably tell that they would not be able to, and LDA would not be able to separate them linearly. Something along those lines. But
Right.
this will be hazy also at
Right.
this point.
So right, okay. So basically in LDA we had assumptions, right? One was that each class conditional density, right? Class conditional density is Gaussian, right? I think so. This is what we make the assumption. But the idea is this, right? So here, when I have mean as 0 and 5, let's say, variance is 1 and 2. So if variance is 1, what is this standard deviation? It's 1, and this is around root 2. Root is like 0.1, 0.414 sort of number, right? So the point is this. So if mean is 0 and variance is 1, your maximum amount of points that are there will be around in this range, like 1 to -1 sort of a range, right? And if it is for the second class, that is with mean 5, it's about 5 minus 1.4 is like 3.6 or something. So 3.6 to like 6.4 or something, right? So basically, so I have my Gaussian distributions like this, in this way, right? So I can easily classify them, because if I project it on this axis itself, so I can always find a threshold which I can say, okay, it belongs to class the this class or this class, right? So here also we cannot make a complete claim that it will definitely be able to classify them perfectly, right? Because what does perfect classification mean? It means that it should have 100% accuracy. Now the point is that for this second class, right, which has mean 5 and variance 2, I can also have points which are in this range, right? For example, let's say when I have a Gaussian distribution, since the density is non-zero everywhere, right? So I can always have a point which is like very far also, right? It is just that it's so rare that hence we say the variance was 2 or whatever, right? So the point is that we say it may be able to classify them perfectly, and we say may because of this reason, that I can have a point which is very far away, which lies on this space itself, and therefore we may not be able to ever classify that point with this LDA method, right? That is in this case. In a similar thought process, when I have mean 0 and variance is means 0 and 1, right? Two classes here. Variance is 2, right? So this can go from minus 1.4 to plus 1.4, something like this. So this is, for example, let's say class 1. Okay, so this is class 1 sort of. and class 2 is, for example, with variance 3, so like about 1.73, something like that, right? So it's going like this, right? So what's happening here is we have a lot of overlap between these two. So if I were to use LDA, what it'll do is it'll basically project it on some linear dimension, right? For example, on this dimension, if I were to do, you will never be able to get a good classification, right? So the point is that so hence LDA will not be able to classify them perfectly at all, right? So this is the reasoning behind the the question and the answer. So any more doubts on this? The person who
सर
asked.
इन अकॉर्डिंग टू फर्स्ट क्वेश्चन आंसर विल मतलब ऐसा कभी होगा ही नहीं कि आंसर डेफिनेटली होगा.
हाँ, नहीं, correct. Because the thing is, definitely you cannot say, because it's always dependent upon the data in the first place. And when you say variance is 2, you don't know what is a max and min, right? Right? So the, that's the most important thing. So if you just say variance is 2, and we also have a Gaussian assumption, so we can never know what is the maximum value that is present, or minimum value which is present in the data. So hence you cannot say definitely.
सो सर कोई भी वैल्यू हो मीन एंड वेरिएंस की, आंसर डेफिनेटली हम कभी नहीं बोलेंगे.
कभी नहीं बोल सकते ना.
एंड सर इसका मे बी एबल टू कब बोलना है, डेफिनेटली नॉट वाला कब बोलना है, इसमें एग्जैक्टली क्या कॉन्सेप्ट रहेगा इसका?
So the point is, we're saying may be able to, because of the fact that I can have, there is good amount of region between these two where there is no data present, right? The amount of overlap that is present between these two distributions will be very, very less. So what does it mean? It means that I will not have, most likely I will not have any points there, right? For example, so what does it mean? So let's say this is your distribution. This is your first distribution, right? And this is second distribution, right? Now the thing is, it's Gaussian. So Gaussian will tell, okay, this particular a Gaussian distribution has non-zero support everywhere. So it is possible that I will find a point of a blue class here. It's possible that I'll find a point of red class here, but the probability of finding such a point in your actual data set will be very, very less. So you'll say, okay, it may be able to classify them perfectly, right?
सर मींस वेरिएंस का रूट लेके हम ये डिस्ट्रीब्यूशन बना दें, अगर मीन दोनों के जो वेरिएंस हमने रूट लेके जो हमने मीन से डिस्टेंस लिया, अगर वो एक दूसरे को क्रॉस ना करे तो हम मे बी एबल टू बोलेंगे.
यस, करेक्ट
है ना. मीन से दोनों तरफ डिस्टेंस हम बनाते हैं रूट लेके, एंड अगर वो क्रॉस ना करे तो मे बी एबल टू, और अगर वो क्रॉस कर जाए आपस में तो फिर डेफिनेटली नॉट बी एबल टू.
करेक्ट. यस.
Okay.
That's the idea. Yeah. Okay. So we'll start the today's topic. So so we had some pending items in the previous lecture, right? So one thing is that I'm sure you guys know that the final exam notification has come. So just make sure that you have reliable network and you try out the on-screen calculator. I think there was a link to that, so just try it out and be ready with how to work with it with just your mouse and your screen and stuff like that. So previous year's question papers will not be given. There's some technical reasons for this, which so if you want to know more about this, you can ask on the Google group. Maybe the course TS can tell you better. So it won't come mostly. Can you please?
Raj?
Can you please? Yeah, who is it? Yeah.
Yeah, so maybe there.
Yeah.
Raj.
Yeah.
Yeah, so I have a doubt. Means you said that you make sure that you have a reliable network, but I think there is an exam. It's a proctor test, right, at the exam center for me. So I think there is no issue of a reliable network, right? Because I'll be anyways giving the exam in a examination center, right?
Oh, it's that way, is it?
Yeah, I think so, because
I thought you have to just make sure that you are in a closed room, something like that.
No, it's not a online proctored exam at my home. I think I have to visit some of the examination centers. There were a list of centers.
Yeah. Then you're fine with this. Then it's not your headache. It's the exam center's headache. Yeah.
Is it online? Yeah. Is it online at home? Can you confirm?
Okay. So have you guys gone through the whole thing properly? Because then that should have the all details.
No, the exam would be held in the TCS Ion centers. all the previous courses and all the other courses are also held there. So,
Right. So it'll be a room based. So this is not something that you need to worry about. So you will have a separate, location to go to.
Sir,
Fine.
please tell week 8's question 1.
1 second. Yeah, we'll come to that. We'll come to that. So yeah, week 9 we had the HMM question we were talking about last time. So the argument there is that, see, Fibonacci series itself in the first place is a this one, what you can say, like a known system in some way. There's a probabilistic, thing required here. So there's no point using HMMs for Fibonacci series, right? So the way that we had built the last time, the HMM, so there's no probabilistic transitions here. So it is all just deterministic, right? So hence using HMM for Fibonacci won't make any more sense than using a normal recursion sort of a loop, right? That is one argument. The second thing was regarding the trajectory of the baseball system. So the more I think about it, it's actually not a purely a Markov model as such. It's Markov control process. So what do I mean by that is, let's say something like this. So for example, let's say if I had, for example, let's say, to model a trajectory of a ball which is, thrown like this, for example, right? So there is no external, external timing events which can affect the ball's, trajectory as such, right? So but in baseball kind of systems, right, you have a thrower, you have a person who's trying to hit the ball and so on, right? So basically what's happening is you actually have like a external control sequences which can change the way your state transitions happen. So that is actually called as Markov control process, right? Markov control process, not just Markov process, because Markov process basically tells you that whatever given st minus 1, I can go to st from regardless of what the previous history of s1 to st was, right? In Markov control process, the idea is that given st minus 1 and given some action that is at minus 1, these two together determine what the next state is going to be, right? So in the case of baseball, for example, if let's say at time instant 10 the action was of hitting, let's say hitting the ball, right, hitting the ball. So what will end up happening is the state that the trajectory that the ball starts to traverse will actually change, right? So the S11, in some sense, the position at S11, right, depends on this action, right? If A10 was hitting the ball, then the position would change, and if A10, for example, let's say was missed by the batsman or something, right, the way your position will change will actually be different, right? So you cannot actually model this as a HMM. That's the other idea here. Okay, hopefully this is clear. Any more doubts on this question though?
Yeah, so the Markov control process and a Markov decision process are the same, I believe, right?
No. So Markov decision process has a reward structure on the Markov control process. So you actually have a RT.
Okay. There is an additional function there, right?
Yes, you have a RT kind of a system. So basically, so you have a reward you get at every time point with because of this transition, and then you so it's called decision process because you can take these actions AT. You can choose in a manner that you try to, like, say, more generally, like, try to maximize your reward in some sense. That's the idea.
So these are not purely deterministical systems, right? You have the initial state and you can predict the trajectory afterwards. It's not like that, right? You need to get the value of actions at every discrete events, right? Discrete points in time.
Yes. Correct. Yeah. So, but what you can do is obviously look at what is the average possible trajectory. That you can always do, because you can always say summation over 80 minus 1 this one, and then look at what is the most probable next state sort of a thing.
Yeah, so sum over all the possible actions, right?
Some are possible actions, right?
Yeah.
Yeah. So Markov decision
Sir,
process.
week 8 question 1 and 6, please.
Uh, 1 second. Okay. We'll do that. Um, we, le- I'll cover whatever has been left last time, so that we can move forward with a clean slate in the coming lecture. Yeah. Okay. Then it was this week 9 question that we had. Week 8 question 4. So again, I spoke to Coach TS. The idea is that you need to assume what the one the mentioned lecture was to be used. So this question was that your ADA boost and gradient boosting algorithms, right? So gradient boosting. So if it is not mentioned, please assume whatever has been mentioned in the lecture, and do this selection metrics for selection for this distance metrics. I haven't gone through it anymore, so we'll see if possible we'll do it next week or not. I'm not sure if we have a next week lecture also, but if we have, we'll see. We'll try to do that there. um, um, Okay, so I had two things to cover today, two ideas to cover today. One was that somebody asked on the group that how do you understand GM as a clustering algorithm? So I think the idea, so the point here is that, see, in k-means the point was that it was a hard clustering algorithm, right? So each point can belong to only one cluster. Here the point is that each data point, let's say xi, belongs to all clusters. It is just that the ratio, or basically the importance of each cluster for each point changes, right? So the assignment probability
Uh,
in some sense
These are the
is
responsibilities, right?
responsibilities in some sense, right? So for example, let's say if you want to know what is the so what is the responsibility in that, basically is basically you look at p of zi equal to k, right? There is a given xi, right? So zi is the the cluster to which you're trying to understand the responsibility of, right? So basically so the probability that this point belongs to this cluster is given by this, and obviously summation over k will be equal to 1, right? So so we have so whatever is the so each point belongs to all the clusters. It is just that how much it belongs to each cluster changes, and that is what is basically the idea of your soft clustering in some sense. Okay. And so here there's another idea here that we can always look at we can also look at this as some sort of a inference mechanism, right? So inference, basically it's telling you that what is the so what is this p of zi given xi, basically, right? So it's telling you that how can I in some sense encode this xi in this space of zi's. Okay. I mean, so when you take this idea further and say, okay, ZAs can also be continuous and all of that, that's where you bring in the ideas of VAEs and other stuff from there. Okay. So this is the idea of inference in these sort of algorithms, where you want to encode your data in some space which is hopefully low dimensional, right? GMMs are also known as are also basically universal density approximators. What does this mean? So we already know that neural networks are universal function approximators, right? So that so this basically means that I can approximate any function to arbitrary closeness, right? To arbitrary closeness. This, in the same spirit, GMMs do this. So GMMs basically tell you that they can approximate any density, right? Any density to arbitrary closeness. So this means basically your probability density to arbitrary closeness, right? And as with as with the neural networks, same issue we have in GMMs, right? So the EM algorithm that is present, it basically falls into local minimas. Plus we don't know what is the right number of parameters to use. For example, same thing with neural networks. Do I choose 2 layers, 3 layers, how many nodes do I choose, what activation function do I choose, and all of these similar issues we have in GMMs also. That is, for example, what should be my number of clusters do I choose, and basically how do I work with the issues that come up with GMM estimations, right? So these two are the points that you should basically try to understand, when it comes to GMM as an algorithm. um, Week 11 questions, do we have any doubts here? I saw some people having some confusion in this. So shall we do this?
Yes, sir.
Okay. So the first thing is yeah. So what are the necessary
Explain that
conditions?
K and K dash.
Sorry.
That K and K dash, two
K and
problems
K.
are there na, on the following graph.
K and K dash. You got it. Got it. Yeah. Okay. Sure. We will do that. Okay.
So
So
question 224 on assignment 11.
yes, I got that. Okay, so this question, by the way, we'll come to that. This question, by the way, have you tried to prove what are these necessary conditions? Any ideas how you would go to prove that? I'm not sure. I think this is the one that yeah. Okay, so I'll just go ahead and give you the idea. So we have this. So basically, what we say, P of x is said to be a mixture, right? So this is your pi k times n of x mu k sigma k. So with this in mind, how do you arrive at this condition that sigma k pi k is 1? Any ideas, any thoughts?
Can we integrate the densities on both sides and see?
Right, that's it. So basically, since it's a valid density, so integral x px dx has to be 1, right? Which implies integral x sigma k equal to 1 to capital K pi k mu k comma sigma k has to be equal to 1, right? Now I can interchange these two, right? And by the way, it's not always possible. Okay, this interchange not always possible, but here we can do, because this particular this particular summation is finite. If it is an infinite sum, then you need to use some other sort of thought processes. Okay, and this is equal to 1. So sorry, pi k is here, right? Yeah, so I can take pi k out of the integral because it doesn't depend on x. Now this is a probability overall density, so this is just going to be 1. So you'll get in summation k pi k to be equal to 1, right? And for every k, pi k has to be greater than or equal to 0. This you can see because this has to be positive always. This is always positive. So from these two conditions, you can see that pi k has to be more than 0. So you're basically adding a finite a finite number of positive values, and those positive values have to sum to 1. That means each of these positive values has to be less than 1. So this is how you will get this from these two itself, you get this less than or equal to 1 condition. All right. Okay, so that's the first question in some sense. The second, third question. So okay. So first thing, we have this here. What is the value of k? So how many of you think it is 3? How many of you think it is 4, and why so?
Sir, please explain some basic concept regarding this density estimation of GMM. Means how we should think about this.
Okay, so if I'm not wrong, I think the confusion is that how do you understand this graph? Is that the issue?
Yes, sir.
So-
even means what does this mean? Density estimation of GMM. So what is this GMM telling us?
So GMM basically is going to tell you the the probability density, right? So for example, so as we saw last time, so it's telling you this in this format, right? Sigma over k equal to this one, pi k n of mu k sigma k. Now the thing is, what you have from the universe is only the samples from this, x, right? So you have some xi's, let's say, which are drawn from this p of x. So what you do is you use these xi's and you try to estimate the parameters, your mu k, sigma k, and pi k, right, using your EM algorithm, right? So using EM, you estimated the best possible pi k hat, best possible mu k hat, best possible sigma k hat, right? Now you say, okay, this is my this is the actual values itself for me, because it is the best I can do. So now you'll plug these values back here and then basically draw contours over it. Contours in the sense where this function is equal to some value, right? So basically it's telling us that if I want to draw a contour in this format, right? So I actually have so all the points in this line have so and so, have some probability p of x equal to some number, and then again these points, all these points here have the probability equal to some number, and so on. So the idea of density estimation is estimating these parameters mu k, pi k, and sigma k, right?
Sir,
Once
x and y axis are two attributes here.
Yes, correct. The two attributes.
And sir, how these contours are probabilities, means where the probability is higher and lower, and how are these contours telling us about the probability?
Okay, so
And probability of what?
probability of x, the likelihood of x belonging to this particular from this particular sample, from your Gaussian mixture model. So okay, so I'll give you an idea. So in terms of your one-dimensional, let's say this is your x and this is your p of x, right? You can actually just draw the probability values, right, in this format. But the thing is, when you look at, let's say, two dimensions, for example, let's say x belongs to r square, right? So it's a two-dimensional data set. So you have x1 like this, x2 like this. So to visualize this probability of x, right, you actually need a 3D sort of a graph. Instead, what you do, you say, okay, I will draw curves on this space, x1 and x2 space, which have the same value for this p of x equal to some number k, right? So that is called as a contour plot. So contour plots are basically a way to visualize 3D data on 2D systems, right? So for example, let's say p of x equal to, let's say, I'll say p of x equal to some 3 or whatever, right? So those points, so all of these points on this x1, x2, all of these points which lie on this particular line have p of x equal to 3. And then, for example, let's say I'll draw one more value for this p of x equal to, let's say, 1 or something, right? And that will go, for example, let's say like this, right? Assuming that p of x is some Gaussian, you'll actually see like circular sort of plots coming up like this, right? So that is the idea of your contour plots. So what this is telling you is that all of these points which are the same color, they have the same p of x, right? This p of x value that you have, that is the same for all of these points. Okay, and thing is, these are Gaussian mixture models, so it will be highest at the center and then basically keep on reducing radially. So so the value at this point, this green, will be lower than the value at this point, which is purple here. Yeah.
So value inside जो कंटूर बना इसके अंदर प्रोबेबिलिटी की वैल्यू सेम रहेगी पूरे कंटूर में.
हाँ, पूरे कंटूर पे your so it's not exactly probability as such, it's probability density. That density value is the same. Yeah.
सर बाहर जो कंटूर है और अंदर जो कंटूर है, तो अंदर में अंदर वाले जो भी कंटूर ज्यादा अंदर रहेंगे उनमें ज्यादा प्रोबेबिलिटी रहेगी.
करेक्ट.
एंड सर जो दो कंटूर के बीच में गैप है उसमें हम प्रोबेबिलिटी सेम मानेंगे.
व्हिच गैप, सॉरी?
जैसे सर एक तो इनर मोस्ट कंटूर्स है जिसमें पॉइंट्स बनाए हैं, वहां पे प्रोबेबिलिटी ज्यादा है.
राइट.
उसके बाद जो बाहर हमने कंटूर बनाए हैं उनमें और अंदर वाले कंटूर के बीच में जो गैप है, उसमें हमने माना है कि थोड़ी कम प्रोबेबिलिटी है.
यस. हाँ.
एंड वो प्रोबेबिलिटी यूनिफॉर्म मानी है, लेकिन हमने मतलब दोनों कंटूर्स के बीच में जो गैप है उसमें प्रोबेबिलिटी हमने एक सेम ही मानी है, एंड वो अंदर वाले से कम है.
Yeah, correct. So the thing is, all the points here, they have the same probability density. That is true. and that value of the probability density is lower than the value that is all for these points, and you can actually see the values here actually. So it's 1, 2 and whatever. It's actually not right. It has to be the other way around. Yeah.
So
Anyway,
inside the contours value are constant या वो decrease होते जाती है towards the boundary?
Towards the boundary, correct.
Decrease होगी boundary की towards.
Yes. Yeah, right. Because it's highest here, and then it keeps on decreasing over radially because of this Gaussian sort of assumption. Yeah.
तो सर हम different कंटूर्स की जो लाइन बना रहे हैं वो बिल्कुल जैसे हम एक्स एक्सिस पे 1 2 3 लिखते हैं उस टाइप से हम एक मार्किंग्स बना रहे हैं कि यहाँ पे इतनी प्रोबेबिलिटी है बाहर उससे थोड़ी कम है तो बीच में वी कैन अंडरस्टैंड कि वो कम होते जा रही है मतलब.
हाँ, it's basically reducing in this format. Yeah, correct.
मतलब if we imagine this as mountains, so these are peaks जो अंदर बने हैं वो peaks हैं बाहर की तरफ लेवल अंदर कम होते जा रहा है. We are going towards the ground.
Yes, correct. We're going towards the ground. Yeah, right.
And we have two peaks here क्योंकि दो contours बने हैं.
Yeah. So two contours are there, but peaks may not be just two, right?
So every contour will have a single peak, as you said. Gaussian distribution है तो बीच में सबसे ज़्यादा रहेगा. And दो contours है तो बीच उन दोनों के बीच में peak रहेगा दोनों का.
No. So 1 second. So let's say you have a mountain which is like this, right? And you have a mountain like this, for example. Right? So you have peak 3. You have 3 peaks, right? But the thing is that so when you look at this level, when you're looking at this level, for example, what you will see is you will see one circle here and one circle here, and it will basically have some other circle coming up here, right? So that's the way you're trying to see. So you can have actually multiple peaks. Yeah.
तो सर जो वो 3 कंटूर्स बने हैं वो इस तरह से 3 माउंटेन्स है जो एक साथ जो बड़ा कंटूर बना है जो 3 जैसा है.
Yes.
जो बीच में 3 जैसा वो ऐसे 3 माउंटेन्स है जैसे आपने बनाया.
Correct. Yes. And hence you basically the answer is 4 here, because you can look at you basically have 3 sort of peaks here and one peak at the one peak here, and basically how can you say it is 3 peaks here? Because you have a kink coming here. If you notice this clearly, the way your probability density is, there is some change happening which is non-smooth, which is not Gaussian in some sense, right? So hence you can see that there are 4 the value of k is basically 4. The value of k is basically the value of number of peaks in your mountain example. So it's 4.
सर मे बी जो कंटूर जो दूसरा वाला है वो पूरा एक ही माउंटेन हो तो हम श्योरिटी से नहीं बोल सकते ना कि उसमें 3 पीक्स होंगे. तो अगर एक बड़ा माउंटेन है जिसके बीच में सिंगल पीक है.
No, but the point is we are saying that all these mountains are Gaussians. So basically they have to look a certain way. So for example, if you only had 3 peaks, how it would look like is something like this. It would have like this, and then you'll have like a straight sort of a thing, right? Because Gaussian, so when you have a Gaussian distribution, so you can basically have a variance term which elongates, which has a difference, like it can be an ellipse also. But the point is this smoothness character will be present in that Gaussian distribution. So that is missing here, right? So hence you say that okay, it doesn't seem to be just 3, it seems to be 4.
Sir, fourth one is that separate circle. That is the fourth one.
Right. Fourth is
सर एंड सर जो एक बड़ा कंटूर बना है जिसमें कंफ्यूजन है उसमें सर जो लाइन है वो एक बता रही है एक लेवल बता रही है. मे बी वी कैन से 100 meters above the ground level.
Okay.
एक एनालॉजी हम सोच रहे हैं. लेकिन उसके अंदर का डिस्ट्रीब्यूशन 3 पीक है, एक ही पीक है, 2 पीक्स है, वो हम कैसे समझ सकते हैं इसको देख के?
हाँ, as I said, so the point is how do I say this now? Okay, so let's say that your mountains right, whichever you have, those have to follow a certain shape in them, right? So if they have not followed a particular shape, then you can say that there's something going wrong, right? है ना? So now when you say that this would have just been three three peaks only, there's k equal to 3, how would the Gaussian how would the GMM look like for this? Would be something like this, right? Though that's the so the I'm not sure exactly how to make you understand, but the point here is that your because of the fact that there is a discontinuity in the way your contour looks like, that means the shape of the mountain is not exactly Gaussian shape, right? And therefore we can say that okay, there are two Gaussians here. It doesn't seem to be just one Gaussian, because if it was one Gaussian, it would have looked in a much smoother way. That's the argument.
सर मींस माउंटेन्स आर नियरली सर्कुलर एंड जब भी दो सर्कल के बीच में हमें एक नेक दिखता है तो हम उन्हें दो माउंटेन कंसीडर कर लेना चाहिए.
Yeah, you're correct. Yeah, right.
तो हमें सर्कल्स देखना है कि हम कितने सर्कल्स लगभग सेपरेट कर पा रहे हैं.
Not just circles, which is the point they're trying to make. They can be even elliptical.
या सर्कल एंड सर्कल टाइप शेप जहां में नेक दिखे वहां में सेपरेशन कंसीडर कर लेना है.
Yes.
दो के बीच में नेक दिख रहा है तो जब पतला हो रहा है बीच से तो हम उन्हें सेपरेट कंसीडर कर लेंगे.
Yes, you can. Yeah, that's the idea. Yeah.
And basically sir k means number of peaks, total number of peaks.
Yes, k is total number of peaks. Yes. Yeah.
Okay sir, thank you.
Okay. Any more doubts on this question? So here k is equal to 4, and what is the minimum value? Very very similar density estimation. Very similar because as you can see, as we discussed that if this was to become like a single one Gaussian sort of a system, you wouldn't have that much difference compared to the current contours that you have drawn. That's the assumption. That's the reading that you can get from this particular density estimation. So k equal to 3 would be the right answer here. Yeah.
सर इट कुड बी 2 अगर हम उस पूरे को एक ही माउंटेन मान ले तो जब हम मिक्स ही कर रहे हैं तो फिर उस पूरे को पूरा मिक्स करेंगे ना.
But how will your contours look like? That's the question. So when you say very similar density estimation, it means so density estimation similar means your contour should be similar. That right? That's the if and only sort of condition. So if you had just assume two Gaussians, you would have like one like this, and you all of this will just become one big blob, right? So these niceties, these points, these regions where there are no points would actually have been lost, and saying that okay, there can be more points here, but there are no points here, right? So so basically we are actually asking in a way a very simplistic question. That question is basically will is this more similar to this or more similar to this? That's the question we're asking. It is obviously more similar to this, and hence this is the answer. With k equal to 3, you'll get this, right? Because very, very clearly it will become one cluster, and here you can see that your these points are forming a unique cluster of them own, because we have like a good amount of gap here. Here we don't have that much of a gap, so hopefully these will get clustered into one. If they were to get clustered into one Gaussian, that Gaussian will basically have like a very broad shape here, and that broad shape is what is being is what will come in this format. Is that
वो दो को मिला के हम एक एलिप्स बना देंगे जो राइट मोस्ट टू है.
Yeah,
उन दो को भी एक एलिप्स.
yeah. So these two will become an ellipse, and the thing is that ellipse will not be very different from this will be least difference from this particular shape, and hence the answer is 3.
Okay sir.
Yeah. So this is the
Raj,
yeah.
I had a small doubt. So you are saying that the smoothness constraints means at the clean position there should be some smoothness criteria that should be following.
Right.
So I think it's a little vague. So are there any mathematical characterizations of the smoothness constraints you were speaking about?
So actually speaking, so ideally what you would want to do is you want to look at the these values, right? Yeah, these values basically, right? So for all of those points, what you would ideally do is you'll form a table like this, right? You will say, okay, under this 4 Gaussian, k equal to 4, and under k equal to 3, right? You will want to look at the values of p of xi, right? So and then compare how this p of xi is looking for between when k is equal to 3 and when k is equal to 4. So and then you can actually compare using either usual MSE sort of things, or you can also compare using KL divergence and stuff like that. So like how different are these two probability estimated probability distributions?
Okay, okay.
Yeah.
Okay, and it's a non-parametric process, right? The Gaussian mixture model estimation kind of thing. It's a parametric or a non-parametric?
It's a parametric, no? Because we have.
It's a parametric. Yeah, yeah. You're assuming Gaussians, right?
Yeah. We were assuming.
But the number of Gaussians you are not fixing, right? So in that
Correct.
sense, it's
No. So we don't say it non-parametric. We say K is a hyperparameter.
okay, like that. Okay,
Yeah.
fine.
So in K means also we don't know what's the actual number of clusters that there can exist. So we say, okay, K is some hyperparameter, and you vary your hyperparameter and see where you have a least inertia or whatever metric that you have.
Okay.
Sir, in question 3, it is asked what is minimum value of K dash. Means basically they want to reduce the number of mountains, peaks as much as possible.
As much as possible, for which you'll get a similar density estimation. Yes.
Means basically it is not they want to reduce it less, they want to reduce more. Maybe they want to go towards 2 or 1.
No. So just because the word minimum here doesn't mean that. It means under the constraint that, okay, for which you will get a very similar density estimation. Because when I use k equal to 2, what will happen is I'll have a shape which is like this, which is very, very different from what I have here.
Yes. Means we have to adjust within a certain limit.
Correct. And that limit is basically that you should have a very similar density estimation.
Sir, please explain question 4.
Sorry. Okay, question 4. Assume equal pi I for each Gaussian model after convergence as in question 2. Okay, so when you have equal pi I for each Gaussian model means, so since you have 4 Gaussian models here, so equal pi I would be each of them having 0.25, right? What would approximately be pi i's for the models that you will get with k dash as in question 3, right? So again, see the point here is what is pi I telling you, by the way? What does pi I mean in some sense? It's the in some sense the number of points assigned to this, right? Number of points assigned to cluster I, right? Number of points assigned to cluster I. So we are saying that, okay, when k was equal to 4, so I had something like this, right? So I had 4 Gaussians, so 1, 2, 3 and 4, and we're saying that, okay, all of these have similar pi i's upon convergence. So here all pi 1 to pi 4 everything is 0.25, right? Now I'm saying that, okay, if I were to have use only three Gaussians, what would their respective pi i's be? Now the point you need to understand here is that they have similar density estimations, right? So what you're trying to understand, what you're trying to see is that the points, the number of points that are assigned to 3 and 4, both of them will combine together to form the third Gaussian, right? So now we're saying, okay, this is one Gaussian, second Gaussian was somewhere here, and the third Gaussian is now consisting of all of these points. So therefore pi 1 will be still 0.25 because the number of points assigned to this cluster is still in the same fraction. Pi 2 will still be 0.25. Remaining all the points are in this third cluster, so it will be 0.5. Right? This is the idea behind this question. Yeah. Okay. Go ahead.
So pi I is basically, we can say, area of a mountain.
Area of a mountain. Yeah. In some sense it is because it's saying that. Sorry, not area of the mountain, but how much of the total area is this mountain covering? Yeah.
It's ground
fraction of
का जो area है mountain.
Fraction of the area, yeah, correct. Yeah.
So earlier all 4 mountains were nearly same area के थे, लेकिन अब 2 mix हो गए तो वो 0.25, 0.25, 0.5 हो गए.
Yeah.
Sir, summation pi I is always 1.
Correct.
Okay, sir.
That's exactly what we did here, right? That's what we proved here. Okay. Fine. So that was the question 4. Um, yeah. So here we have for a set of points given in orange, the density estimation of a GMM is given below. Um, we should answer question 5. Okay, fine. So what is the problem evident in the image? Okay, so how many of you are not clear on this? Why is this not the answer? Why do you think anything else could be the answer? Any thought processes? Oh, by the way, there was one person I think who said that he assumed that this is basically these points are basically points which are after clustering, right? So and they are of the same cluster and so on. But then you can always make a question here also though, right? But here you assume that they are different clusters. So I mean you need to use some bit of an imagination. But the point here is this, that these are all the points given to you, and the estimation is using two Gaussians. As you can see, like these are very clear. I'm trying to use two Gaussians, but the Gaussian estimation that I mean the mean and the variance that these two Gaussians ended up having was in this format, right? So we had points like this, and these are basically two mountains here, right? So
Sir, what are these, sir, yellow dots here? So
the,
जो yellow dots है बने हैं.
these are the points of your the points that you want to cluster your data.
तो जो डेटा पॉइंट्स है x and y के.
Yep.
तो सर वो तो सर्कुलर फैशन में है ही नहीं, जैसे पिछली लास्ट क्वेश्चन में दे वर इन सर्कुलर फैशन.
That is exactly what the answer is. So they are not sampled from a Gaussian distribution, right?
सर इफ दे आर नॉट गॉसियन तो हम उन्हें सर्कुलर बना क्यों रहे हैं? हम जो कंटूर्स बना रहे हैं वो सर्कुलर नहीं होने चाहिए, वो भी ऐसे ही होने चाहिए, सेमी सर्कुलर टाइप.
Correct, but Gaussian mixture model will always give you circular clusters, no?
मतलब सब हमने फोर्सफुली इंपोज कर दिया है गॉसियन मॉडल को इसके ऊपर.
Correct, exactly.
Sir, Gaussian distribution basically means symmetrical mountain, we can think.
Yes, yeah, it is a symmetrical mountain. Yep.
But not with a peak. Peak is also basically rounded kind of thing.
Yeah, peak is rounded. Yeah.
Okay, sir.
Raj, this example looks like a very pathological kind of data set. So, which algorithm would actually classify this? Not any linear mode. Kernel-based methods can do it, right?
It's exactly what I was coming to. So I was thinking that if for example, for some reason you want to apply GMS for this, ideally what you could do is you could try to transform into a different space. So I'm assuming R theta space again should be more than sufficient. For example, using polar coordinates, you might be able to understand that you have angles changing. The way your angle is changing, that might be good enough. Or you can use some other kernels, for example, and transform it in that space, and there you can apply GMM. Maybe that's one way to go.
Okay.
Yeah.
Sir, question 6.
Yeah. What can be done to see what is the question? The question is what can be done to get a better fit, right? We're not asking okay, what all can you do to solve the problem? I want to use Gaussian mixture model. So what can you do to get a better fit for this particular data set, right? So if I were to increase k, right, how would that help? Any thoughts?
Sir, we will have more mountains, so it could have been better.
Yes.
मतलब उसमें हम ऐसा मान लेते हैं कि 10 माउंटेन्स है जो पूरी लाइन बनी है.
Yep.
क्योंकि डिफरेंशियली तो हर डिफरेंशियली हम उस एरिया को 10 पार्ट्स में डिवाइड कर देते हैं उस सेमी सर्कुलर लाइन को, और फिर बोल देते हैं कि सब माउंटेन्स है, तो
Each of these are
हो सकता
mountains.
था.
Exactly. So this one mountain and this one mountain, one mountain.
Yes, sir.
So and the thing is, since we're using Gaussians with estimated, you can estimate its mean and variance. So these variance can be elliptical also, as discussed before. So I can choose, for example, let's say 8. K equal to 8. I'll be able to fit the data the best when I use k equal to 8. Right? That's the idea here. So increasing k will help you to get a better fit. Right? So this is the this one. The remaining, I think, so 8 and 9, I guess. So 9, yeah. So it's not KNN, it's K means. So mostly there'll be a grace for this question. And this again, I think from the lecture, I think you should be able to get this from there. And soft clustering we just discussed. Samples are assigned probabilities belonging to a cluster. Okay, so this completes week 11. Any more questions in this particular question in this particular week?
I had a small doubt during the lecture when the person was actually making us understand that there were 3 clusters of different colors, right? And he was trying to assign responsibilities. And because there was no pointer on the videos, I was not able to make out which cluster he was actually referring to.
Okay.
So that was a bit confusing. Means I can point to you the exact time means when that was happening,
Okay.
but it was very difficult for me actually. So are there any possibilities to clarify that? What he was actually referring to? The Bishop's book, he was referring to 3 particular clusters.
Yeah, I remember. There's something like this, no?
Yes.
Yeah,
And he was trying to assign the responsibilities. And first he was telling that they will not be inferred properly because of misattribution. But I was not able to get which figure he was referring to. He was not telling right or left. So
Okay.
probably in the class it was okay, but for us there are no pointers on the screen, right?
Got it. ठीक है. I'll ask the course TAs. Maybe we can edit the video in some sense, or we can ask them to record it again. We'll see.
Sir, in GMM it is either circular or elliptical.
Yeah, correct.
Sir, week 8 question 1 and 6, please explain, sir.
Week
8.
week 8 is it? Okay.
Question 1 and 6.
Yeah, just a minute. Let me just check what else things are trying to complete. Do we have time? We don't have. Okay, fine. So I mean, there are some points here, some questions here. You can just go through it in case you're interested, to understand what else is there. So week 8 question, we'll do that. Week 8 question. What is week 8? Oh, this question. So we have done this before. I'm not sure if you were there in the lecture or not. But maybe so refer week 9 or week 10 session video.
Sir, I was
have
not
done,
able to join.
so yeah,
I
so
don't know why.
we have recordings, right, of all of this. So I would suggest go through it once, because we actually discuss this in good detail, right? So and I don't think I'll be able to do justice in 5 minutes to this.
So question 6.
Yeah, this also we discussed in that this one. So I mean, I would say just go through it once. In case it's not clear, obviously we can do it on the Google Groups platform. But I think this was done in fair amount of detail.
Sir, week 7 question 4.
Just a minute. I think it was week 9, if I'm not wrong, where we discussed these questions. Oh no, not this time. Week 10 maybe. Yeah, so assignment 8 and 9 questions are discussed here. So this is the question 1 that you're talking about, and I think this is the question 6 also. We had a part of it. Yeah, this is an A assumption. So please go through this. It's discussed in good detail in that session. Yeah.
Recordings are there, sir, right?
Sorry.
Recordings are there,
Recordings
or
are
only
there.
this one?
Recordings are there. Yeah.
Sir, question 4, week 7.
Question 4 is it? Oh, practice 1. Okay. No. Sorry. You wanted the
Main assignment. Quiz.
Oh, okay. Question 4. This one.
Yes, sir. In this question, it is saying that we have 10 classes and 5 folds. So what if जो सर लास्ट फोल्ड होगा, अगर ऐसा तो बोला नहीं है कि सबका डेटा बराबर होगा 10 क्लासेस का, तो अगर किसी क्लास का डेटा बहुत ज्यादा हुआ और बाकी सब क्लासेस का डेटा कम कम हुआ, तो जिसका डेटा ज्यादा हुआ अगर वो जब उस पर ट्रेन करेगा 80% मॉडल वी विल यूज फॉर ट्रेनिंग एंड 20% फॉर टेस्टिंग। तो अगर किसी क्लास का डेटा बहुत ज्यादा हुआ तो 80% में वो भी ट्रेन हो जाएगा, और अगर वो ट्रेन हो गया तो फिर उस पर एक्यूरेसी भी दे देगा वो। तो जो ये बोल रहा है 0% एक्यूरेसी, ये तभी होगा अगर हम अज्यूम करें कि सबका डेटा बराबर है, पर ऐसा बोला तो नहीं है।
So in case if it's not told, then just assume that there's same sort of the
Quantity.
similar quantity, yeah. Because if it is not similar quantity, then they will tell you explicitly that okay, there's a class imbalance, or the class prevalence ratio is about so and so and so on and so on. Okay, if it is not given, just assume that they're roughly similar, and hence this will then end up holding.
Okay, sir, week 4 question 4.
So if you have these sort of questions, I would suggest put it on the Google group. No, it'll be a simpler thing to do, because then I know exactly what to cover. Yeah, go ahead. Yeah, what is the thing? This one is it?
सर बेसिकली इन एग्जाम वी विल नॉट हैव, मतलब हम कोड तो कर नहीं पाएंगे। और सर ये ऐसा बोलते हैं कि आप ये जो जैसा दिया है कि डिग्री 3 C1 गामा 0.1, ये तो सर कोडिंग क्वेश्चन है ना एक तरह से।
This is a purely coding question. Using this sort of a kernel, trying to classify and all, it's just too much. This sort of things won't come in the question. Yeah.
So सर एग्जाम में इस टाइप के क्वेश्चंस नहीं होंगे ना, क्योंकि कोडिंग क्वेश्चन। सर कैन वी सॉल्व दिस बाय हैंड, मतलब या इसका कोई छोटा वर्जन अगर क्वेश्चन का एग्जाम में दे सकते हैं क्या, जिसे हम सॉल्व कर सकते हैं कैलकुलेट करके?
Yes. So for example, like you may just have like 2-3 points or something, and they'll ask for example here like this, right? You had a question like this, right? So where you have a 2-dimensional data set, and what they'll say is they'll say, okay, use some sort of a basis function and try to apply the support vector machine, this one. Yeah, that's
बेसिस फंक्शन तो नहीं है ना इसमें, तो सी डिग्री गामा की वैल्यूज गिवन है, तो इस टाइप का क्वेश्चन कैसे सॉल्व करना चाहिए अगर एग्जाम में आता है इसका छोटा वर्जन? तो
see, degree tells you what is the basis function in some sense, right? Because polynomial kernel with degree is the basis function, so that's the basis function. C equal to 1 is, I think C is the what is that, the weight of the misclassification rate, if I'm not wrong, and gamma is something else altogether. So no, so these sort of questions won't come in your question in your handwritten sort of a thing in your online class.
And sir, question 6, 7 also of this assignment itself.
Train a linear
Can we solve this by hand? This question or its variation that can come in exam?
No. See, a variant can come, right? Because okay, let me give an example. The worst case. So, for example, let's say, yeah, you're given a point like this, right? So let's say you're given, you're told that you have points like this. Let's say this is 2, 2, 2, 0. 0, 2, and then 0, 0, and let's say this is belonging to class 1, some one class, in this second class, let's say these two are the second class. Now they'll say, okay, start with the perceptron, some weight value perceptron, for example, let's say 0, 1 or whatever. Apply the perceptron algorithm to classify these two classes. Right? Now, since they are linearly separable, your perceptron algorithm should, will converge to some value. You just need to find what that value is. So, what is the weight value that will end up, classifying these? That's that's possible. That's a valid question to ask.
So how can we solve such questions?
By applying the perceptron
Please,
algorithm.
can you give a demonstration?
Okay, so W, you need to find out the in perceptron what's the update equation is that you need to see whether it is whether the given thing is classifying it or not in the first place. Okay, so let's say you have, so what we'll do is we'll say W transpose X, you'll try to find this value, right? Because in the perceptron algorithm, right, what are we trying to say? We're saying we'll see that whether this W transpose X, right, is it +1 or minus 1 if I'm not wrong. And
So what
then
is W telling us here?
sorry.
What is W 0 comma 1? What does this means here?
So okay, so x is a two-dimensional vector, right? What will the dimension of w?
So I think are this they are similar. I think.
They have to be the same, right? Because your w transpose x has to be a number.
So basically, by looking at this figure, can we tell W?
No, we cannot, because a perceptron algorithm depends upon what your parameters are, and it can find different w's here. For example, it may
So
find
what?
this, it may find like this also, and so on.
So W 0 comma 1. What was it telling us?
So w01 is the initial assumed vector. Let's say these are your initial parameters for your perceptron algorithm. So okay,
Means, sir,
one
how to
second,
visualize this?
one
Please.
second. Are you aware of perceptron algorithm?
Sir, I know that perceptron can classify linearly separable points.
How?
Sir, that exactly I don't know.
Then matlab, you need to see the algorithm, no? So I would suggest go just see what the algorithm is. Okay, what are the steps there, and apply those steps for this particular problem. You'll be able to find what your w should be. Is that
Okay.
a valid request?
Okay, and sir, one more request that last year's pass ratio of exam of this machine learning was only, sir, 22%. And sir, many students do this course because we do this for credit transfer to our university.
Yeah.
And sir, this passing rate of 22% is very low. Means for different subjects it is 90% or 80%. So sir,
Okay.
this was one request that please set paper somewhat easy because passing ratio of 22% is very less. Means it is very less if we compare to other NEPTEL courses. Mostly there are 80, 90 plus.
Okay, but I can relay this information to the the course TAs and the professor, but I don't have a control over it.
Yes, sir. Please forward this request that
Sure.
many students do these courses for credit transfer to their universities. And 22% means very low. And sir, basically our career is on stake. So I request you to please set easy paper that if you forward this request.
Yeah, I can forward
Because
the
it is
request.
compulsory for us to pass this exam this semester.
I can forward the request. That much I can guarantee. Yeah.
Yes, sir. Thank you, sir.
Yeah. Okay. Anything else? Anybody else has any doubts?
Raj, I
Yeah.
had a very small doubt. So you were telling that the GMM actually was if I remember correctly, that NNs were a universal function approximators, and GMMs were a universal density estimators, right?
Correct.
So densities are examples of functions, right? So NNs can also be universal density estimators. That's my point.
NNs can also be universal density estimators. Okay. So in a way, yes, because then you can say that
Because
it'll have to be a
density
bit.
is always a function, but not the other way around. A function may or may not be a density, right?
That is true. It is a function of x, though. That's correct. Okay. I see your point, but I'm a bit confused actually. So, is that the right way of putting it or not is a question. But I mean, you can use neural networks to estimate the parameters of GMM, and that becomes an even more powerful thing. But exactly, would it be right to say this or not? I'll have to think about it.
Yeah, because it's then going from a totally a parametric to a non-parametric estimation technique. Yeah, it's totally different that way.
Yep.
Sir, week 10, question 3.
Sorry.
Week 10, question 3.
Week 10, question 3. Okay. What this question?
Sir, means are all these questions after these related to this coding of SK? All these questions after, yes, sir. So all these questions after question 3 and all these questions afterwards are related to coding.
Yep, correct. Yes.
So, sir, means what kind of question from this portion can be transformed to come in exam? Because coding questions won't come directly.
Okay. Help me understand. coding is also, after all, some algorithm implementation, right?
Yes.
Okay. So we code because we cannot do we cannot take so much data at once in our small heads and try to, you know, calculate the values with our pen and paper. So the idea of coding, the idea of computers, is basically you want to scale what is already present, right? So basically, just so that it becomes applicable to the exam, the idea is that you will have a similar algorithm but given on a simple data set, on less number of points, on less dimensions. For example, nobody will ask you to cluster points which are in 10-dimensional data space. Rather, it will be like a 2-dimensional data space which you can even visualize, by the way, right? So that's the idea. So if you know the algorithm, coding is just because you want to scale the algorithm.
Sir, please explain question 3, means basically how to solve this on pen and paper of the small version. Question 3, week 10.
Okay. Okay. What is the K-means algorithm? Let me just, can you help me understand what K-means algorithm is?
Sir, basically it's a clustering algorithm.
Right.
So, sir, clustering means basically we classify the points that are near to each other, and we then try to classify. Means basically K, we decide that this will be the number of clusters, and then, sir, after that, what I know that some concept of centroid is used, but after means if K number of clusters will be there and centroids will be used to cluster. This much I know.
Okay. So in K-means, the idea is first you initialize some cluster points. Initialize K cluster points. So not cluster points, cluster centroids, right?
So this would be arbitrary.
This would be arbitrary, correct?
Okay.
These are arbitrary. So for example, let's say you have 6 points like this. Okay, these are 6 points, and you can initialize any of, for example, let's say they tell you, you know, use K equal to 2, so you can use any of these 6 points to give them as some K. So this, let's say K1, I'll choose this as K1, I'll choose this as K2, for example, let's say. Okay. The next step is basically you look at all the, for each point, right? For each point, what you do is you find out the distance from both the clusters, K1 and K2. So cluster 1 and cluster 2, right? And you basically assign the point to that cluster which has the lowest distance, right? Third step is basically you update your cluster centroids, right? Centroids basically here means your mean over the data, mean over whatever is there in that particular cluster from this second point that you got, and you iterate over this, right? So what you will do here, for example, let's say you have 6 points here, you have K1, K2, you chose for the, chose these two. You will find out, let's say you have your point 1, how you can do it is like this, yeah. So you can form a table like this, point 1, point 2 up to point 6. This is the current cluster K1 and K2 points, right? Find the distance. You'll find 6 into 12 distances you will find, and then you can basically see, okay, for this particular point, which is it nearest to? If it is nearest to K1, you'll say, okay, this is cluster 1. Otherwise, if this is nearest to cluster 2, you'll say this is cluster 2. This is a cluster 1, and so on. This is your second step. Third step is you'll update these cluster points. So you'll say now again, no, K1 is going to be the mean of these points, whichever were assigned C1 in this particular iteration. Right.
So step 3, what you said, basically we assigned every point to K1 or K2. So we have initially 2 cluster. Then update the cluster means what we will do in that.
So basically, once you have assigned points to some cluster, let's say P1 was assigned to cluster 1 and P4 was assigned to cluster 1, and remaining all were assigned to cluster 2. So your new centroid, that is your new K1, is going to be P1 plus P4 by 2. And K2 will be equal to P2 plus P3 plus P5 plus P6 by 4, because the mean over these points, right? So
okay,
now you
for
have
both the coordinates we will do this.
For
For
every
both the coordinate
for both the
levels.
coordinates, correct? Yes, yes.
Okay.
Mean over each coordinate, and then so once you have this, you have your new cluster centroids. You repeat this process until where you repeat this process. You have three ways of understanding where you should end a particular k-means algorithm. Either you can look at points stop shifting their cluster assignments, or you can look at are the k1, I mean are the cluster means not changing much, right, between two iterations. Or you can look at for some sort of inertia metric and say, okay, has it not changed too much between two iterations, and so on. The easiest way to look at it is, for example, this points sort of a metric, right? And in case they haven't mentioned, if they have mentioned some metric, use that metric and stop the algorithm.
Points means points should stop shifting.
Yes. So, for example, let's say in this iteration, I got P1 and P4 in the same cluster one. In the next iteration, I still got only these points in this cluster. That means the k-means has converged. You can stop there.
So, sir, even if the centroid is changed, but we are getting the same clusters, so we will stop there.
Correct. If you get the same points, it means the clusters are also don't change. That's in a way inconsequential, but yeah.
And sir, then basically it's asking in question 3, what is the accuracy of the resulting label?
Hmm.
So, sir, after that we have made clusters. How will we find the accuracy of the resulting labels?
That is given in this idea, right? What is the prediction class? Again, see, we have covered this idea in the week 11, I mean week 10, week 11 sort of a thing. So I think if I'm not wrong, you need to go through each of these methods properly. Point number one. Point number two, you need to go through the recordings at least, because we have solved each of these questions in much detail. And also we have discussed exactly what would this label prediction be, how to compute this, etc., etc. So I mean, this is not the level of preparation that you should be at this point of time. 29th is your exam, right? So I would suggest gear up, try to understand exactly what each algorithm is, because computers are just a substitute. You need to know what the algorithm is doing for you to be able to work on it.
So, accuracy basically means number of correct points as expected divided by total number of points.
Correct.
And sir, here RA&D index, sir, it is given A plus B. Sir, please explain this.
I would suggest go through the video, please. I mean, that is, we have discussed all of these points there.
And sir, for exam, if we go through the assignment, so is it enough to pass?
Mostly yes. Your questions will be similar in similar spirit of what has been asked in the assignments. Yeah.
Okay, so sir, all your recordings would help to solve the assignments, and that would be enough to pass the exam.
Yes, ideally yes.
Okay, sir.
Any other doubts? No? Okay. So we'll mostly meet next Saturday again. And if possible, I'll either we'll cover the next assignment, the RL reinforcement learning assignment questions, or we'll look at some recent advances. I mean, some other algorithm, like for example, it's a TD learning or Q learning in RL. That'll give you a flavor of what is happening in the RL field, right? Okay.
Sir, please forward that concern that low pass ratio only 22%, and many
Yes.
students do for credit transfer. So please make paper easy this time at least.
Yep. Sure.
Okay. Thank you, sir.
Yeah. Okay. ठीक है. We'll meet next Saturday. Thank you.